All right, line S1, we're taking a look at learning task number 2, where we're going to start to describe some of our HVAC components. And really what we're looking at inside of this one is going to be a commercial HVAC type of system. There are two main forms of commercial HVAC systems. One of them is going to be built into the actual building itself. The other one is what we commonly refer to as rooftop units. And those rooftop units are going to be those tan or gray boxes that you see on the flat roofs of commercial buildings. Those boxes actually are designed as part of this system. Right over here, I just want to go and take a look at what we have here. We have an exhaust air, and we then have got our supply air. Over here, return air and outside air. There's 4 air components. The whole point of HVAC is to go and heat and cool. What we will see inside of here is that the bulk of our air is going to go and follow the path from inside of the building. We are going to go and accelerate it through here and then drive it, filter it, heat it up, or cool it down as it passes through these 2 components over here, which are going to be radiators. We'll go a bit more in depth in that in a little bit. But then we pass that back into the building itself. And then it goes through our working and living spaces, etc., and then cycles back up and through like that. That's the way that things normally happen inside of a built-in type of system. We do also have another alternate route where we can go and divert some of the spent air, depleted of oxygen, got odors, dust, things like that inside of it, and we can take in fresh outside air to go and make up, as it's called, for what we've gone and expelled out of the building. In a commercial built-in unit, we see this all done through the actual ducts that are going to be placed, cut into the side of the building, those big louvers. On a rooftop unit, what's actually happening up there is that this return air and this supply air that we see are going to be built into the roof itself. So during the actual build of the building, you're going to go and see 2 identical squares that are going to be placed side by side into the roof, 2 cutouts. One of these cutouts is going to go down into the building where it's going to go and connect to my supply air. So it's going to go and supply the air to the rest of the building. The other one of these is going to go to my return air. And all that happens is that that rooftop unit gets placed over top of those 2 components over there. And when the rooftop unit is on top, let me just actually redraw that just a little bit better. When we get that all the way onto there, what happens is that my rooftop unit is going to go and contain all of these components. So it's going to go and take the air in, it's going to be segmented, it's going to take the air in via fan, and then that air will travel from here, it'll travel through some coils that are either going to heat it or cool it, and then it's going to go and travel back down into the building like that. Once again, a little bit of makeup air is also going to go and happen inside of these, meaning we're going to expel a little bit out, and then we're also going to go and take a little bit of fresh back into our units. But they are identical systems. Just one is built into the building itself, this whole one here, whereas the other one, we just crane these things onto the roof and we just hook up our thermostats and our power to them. Inside of a lot of smaller commercial, we're going to have multiple rooftop units for different zones. Inside of a larger commercial that's got a built-in, we're going to go and have one master controller, and then we're going to go and individually control coils inside of the zones, whereas this, if I'm dealing with rooftop units and I got a building that's got, let's say, a little bit of warehousing and some office space and some, manufacturing area, what I'll do is I'll have a rooftop unit for each one of those ones, so that the office temperature can be separate from the warehouse temperature, which can be separated from my manufacturing temperature. Okay, so that's what the overall view of the system itself actually is. The layout and the wiring inside of here is going to be run in a lot of cases by separate trades. We deal with a lot of the power wiring. They're going to deal with a lot of the control wiring that they're going to take care of. And in some cases, we end up having to place in all the conduits for them, etc. Sometimes power to components, but they will take care of the actual units. If we take a look at this, what we see over here is that we have a hot water supply and we've got a chilled water supply. For a built-in unit, we will have a chiller that's going to be on the roof. We are also going to go and have boilers that are going to go and provide hot water. And then I'm going to go and have motorized valves over here. Those motorized valves are either going to allow cold water to go and flow through its coil. The coil is just a radiator, same as the radiator inside of your vehicle. It's a place where we can go and pass air through, but we're also able to go and run water through, kind of like the heat exchanger that we saw inside of our residential. This one over here, my heating one, would go and pass hot water through. So if that motorized valve for either one of these is going to be open, it will go and either heat up or cool down. And then that hot water returns back into our system, same as our cold water returns back into our system as well. These are the two main ways that we provide heat inside of these units, and we will have a set of these inside of every single zone inside of there. Some cases, what we don't have is alternate ones. We don't have a heating coil and a cooling coil. Some cases, we're going to only have one single coil, but we are going to go and select with a three-way, with a mixing valve that we are going to have, so that we can go and select whether we are going to be diverting in hot or whether we are going to be diverting in cold. So it's similar to how you set temperature when you go and have a shower or something like that. We can then just adjust the temperature of the water that's going to be coming through that single coil, and then adjust the air temperature as a result. Looking at my system overall, I see that I've got a number of sensors that are going to be inside of here. We'll just go through these really, really quickly. First one that I'm going to see is going to be outside air. We're going to measure the temperature of the air that we will take into the building so that we know whether that outside air is either too hot in the summer or too cold in the winter, so we know whether we need to go and heat it up or not. Then I'm going to go and take that past my dampers. Over here, I've got a damper motor. The damper motor is going to go and adjust a set of louvers here and here that are going to be interlocked. So as I close this, I would have to open this because we can't, overpressurize our system. We're also going to have another one up top here that's going to be off the same control. So this is all going to go and adjust. If I start closing down the dampers here, then I'm going to go and exhaust more air out and have to pull more fresh air back in. Whereas if I go and block both of those, then I'm going to have to go and have this wide open so the air can go and travel all the way through. 3 over here, MP, that's going to be a minimal positioning device just because we have got laws that state how much fresh air needs to go into a building for health and safety. So this is going to go and set what the absolute minimum position is. That will always be a tiny little bit open, so we're always getting a little bit of fresh air into there. The MA, mixed air controller, that I'm going to have over here is going to go and now take a look at what am I recycling for air versus what am I bringing in fresh. All of that air comes in through this section over here, which is a filter, and gets its speed boosted through a supply fan, and after it exits that fan, we measure that temperature. Based upon the amount of mixed, the internal building air, and the amount of fresh air I bring in, I'm going to have a temperature. And that temperature over there is then going to get fed to my control system, which is then going to go and adjust based upon what the room temperature itself actually is. The motorized valve, we've explained what those are. Those are going to just let cold or hot water through these things. The room thermostat is going to go and measure, it's going to measure the room itself. It's going to compare that with what my air is inside of the ducts. And if the air inside of the ducts is colder than what the room wants to be, it's going to go and heat it up. It will fire my heating coil at that point. Conversely, if the room temperature, what I'm desiring, is lower than what I'm getting through my supply, it's then going to go and fire my cooling coil so that we can go and get cold air through there. Supply air, low limit controller of my supplier is also going to go and get connected so that I don't go to too low or too high. There's going to be safeties that are going to be built inside of here so people can't, run these things out of limit. And one of the other ones that we are going to go and have is going to be this free stat. The free stat is in there just to make sure, because we're dealing with water, and even though that water is going to go and have glycol or other forms of antifreeze inside of it, we need to make sure that that water is not going to freeze, because then all of your pipes are going to burst. Have you ever been inside of a commercial building that's had a power outage in the middle of winter for a couple of days? You have ruptured pipes all over the place. It can lead to some massive costs inside of there. All of that is going to get forced out there, and then my return fan over here is going to pick that all back up again and then force it back through, either expel it from the building or force it back through one more time. These two fans provide all of the air movement itself. The rest of this is going to go and provide my temperature regulation. Fans that are going to be placed inside of these are usually going to be our responsibility to bring power to. They usually will have a contactor over there as well that the HVAC technicians are going to go and deal with the controls for, but we will bring the power over to the actual fans. Different types that we can go and have: centrifugal, which are going to be kind of a low speed, tube axle and vane axle type of fans, which are going to be high pressure, high speed types of fans, and then propeller fans themselves. They do have a relationship to do with our horsepower and with our airflow. So they lay it outside the book in the simplest terms. It's still somewhat confusing, but your airflow is going to vary directly with your fan speed. You increase the fan speed, you're going to get more airflow out of it. Doubling your fan speed doubles the airflow. That's straightforward. Static pressure varies with the square of the fan speed. So if you double the fan speed, you get 4 times the static pressure. So fan speed doubles, 2x speed equals 2 squared x my static pressure that I'm going to have. Static pressure is just going to be the relationship between the pressure inside of something to pressure outside of that. If you overpressurize your ducts, you end up with rupturing. You end up with this noise. Everybody's heard that, inside of buildings, you get those creaking and, that kind of metallic clunking of ducts expanding and contracting. Power is going to go and vary with the cube of the fan speed. So if you double your speed, 2x speed over there, which got you 4 times the static pressure over there, you need to go and have 8 times the horsepower. Requires. It doesn't create, it now requires 8x, oops, or not 8, I'll do 2 cubed, requires 2 cubed, which is your value of 8, the horsepower. It takes a lot more work to go and square up with your static pressure and double your airspeed out of these things. It's a misunderstood thing. It doesn't seem like it takes a lot to go move air, but when you're moving air inside of confined spaces like ducts, there is absolutely a massive demand on your horsepower. Once again, if you're working with one of these systems, if it's undersized, they're going to have to change the motor. If they change the motor, you're usually looking at a significant size change to the actual conductors that you're going to place inside there. Oversize your conduits for these things. I've dealt with it in the past where, stuff has had to go and get changed. The engineers are not always correct. If it's something that results in a drastic change, this over here, that we have 8 times the fan horsepower, we could be going from something, we'll just go and give this thing a 1 horse all the way up to an 8 horse. That's fairly significant. Now compare it to if you have got a 5 horse going up to a 40 horse. That is a huge difference. So leave yourself that little bit of room based upon changing your air speeds. Dampers also are sometimes referred to as the louvers inside of here. 2 main types that we are going to deal with. We have got a hose blade where these things are always going to have a direction that is going to want to get forced open, right? So whether we got air pressure pushing from that side, it's going to want to push into there, helping it to open. If we have got like that, it is going to be pushing in there. We use these in a lot of places where we've got dual direction feeds because we're always going to go and have one that is going to be helping as we go through there. The other one that we have is going to be parallel blade. Now this is a poorly drawn parallel blade one here where they're showing that the hinge point is in the center of each of my dampers themselves. There are some of these ones that are going to be like that, in which case it's going to be an equal amount, that we are going to go and have a pressure working for or against whenever we open or close them. However, we've got a lot of other ones where what it is something like this, where each one of those blades is going to be hinged at the top. These are like one-way valves, like a diode inside of electronics. They are going to be really great at passing air through in this direction. They're going to be terrible at passing air through in this direction because it's going to catch those, and because they're hinged up here, it's going to tend to want to go and flatten those, tie those things down. Yeah, is there anything else we need to have? Not a whole lot that I want to talk about. We do have damper actuators. Damper actuators can be either mounted internal to the duct or external. This one over here shows an internal one. You will have to provide power to these ones as well. They will be on your prints. So if I take a look at this one here, it's going to go and have my duct like that goes around it. Anytime that you see those doors on the side of ducts, they're going to be like a riveted in type of door that's open and closable. It's usually because we've got dampers inside of there, or a coil, or something else that needs servicing next to it. We need to be able to go and access all electrical boxes and controls, including our junctions onto motors. So if there's a motor, there has to be an access plate for that thing as well. Some will be mounted internally. Other ones, they look kind of like a tombstone. They're going to be mounted on the side over there. None of these actuators tend to be really fast. They tend to be very, very strong. Like they got a phenomenal amount of torque to go and counteract the static pressures that are inside of these ducts, but they don't operate really, really quickly. Most of them are also going to go and be powered to actuate and spring returned. Not all, but a lot of them are going to do that, which means that they will have a default position. The spring return does not mean that it will necessarily spring close. It might go and spring open in some cases, whereas others are going to spring close. That really depends upon the orientation. These tombstone style that you'll see on the side of ducts, what they are is they're a through shaft, and based upon the rotation that you are going to place them, like physically, I could take this thing off, spin it around, put it back onto the shaft in the opposite direction. That will now hold the spring pressure in the opposite direction. Makes them really handy for, setting stuff as open or cold. All right. That's going to be my components that we saw inside of the first one over here as far as my fans and then my dampers over here. We've got the mixed air damper. We have got these ones here. These now that we've talked about the dampers, let's talk about these off of there. The normally open versus the normally closed. NO means that it's a normally open type of damper. In other words, if I get a power failure, my spring is going to go and open this thing up so that we can at least get the maximum amount of air that floats around the building. It's not going to be pushed because power's out, return air and supply fans are down, but at least I'm not choking off any sections of the building. My external ones are going to be normally closed. The reason that we have these normally closed is because if you get a power failure in the winter, what you don't want to have is you don't want to have these wide open and then you're getting, an Arctic wind that's coming in and hitting this chilling coil because it's going to freeze that thing up and then it is going to go and rupture. Freeze stat can't do anything at that point because you're dealing with a power outage, right? So we have these that are going to be set as normally closed, these that are going to be set as normally open inside of here. Okay, let's talk about the hot and cold water that we are going to go and have inside of here. The hot and cold water is going to go and come from two places. Either it is going to be heated through boilers, electric or gas that we are going to have, or we can go and heat it through other means. We do have, some buildings that will use alternative fuels or might go and capture solar energy. My cold is ultimately going to have to be chilled somehow. Now, we have got a little bit of free chilling that we can get. Free chilling would be where it's in the wintertime, and I'm actually going to go and run that water outside to go and chill it down, but usually we're not trying to refrigerate in the winter. Usually we're trying to go and heat the things up, whereas in the summer, we're going to be trying to go and refrigerate. We wouldn't want to take that water outside necessarily. If I look at a commercial building that is running water supplies inside of there, what you'll see on the roofs of a lot of them is going to be a large louvered structure. It's going to go and have, a bunch of big louvers. You see it pretty much every movie where there's a chase scene, everybody always runs to the roof and there's all these big structures up there that have got these huge aluminum grills on the side. A lot of those are going to go and be chiller towers. And inside of that chiller tower, literally what's happening is we're exposing the water to the open air so it can go and release its heat. If we're capturing heat with that water in the summer or something like that, what we want to do is we want to take it, release as much heat as we can, and then take it back. So what we'll do is we will actually pump it, and then it's going to go and cascade over a series of baffles that are going to be inside of there. What those baffles are going to do is they're going to break up what we refer to as the laminar flow, the way that the water would otherwise be flowing through there. And this is all happening inside of that tower. It's not splashing out or anything, but it's going to break it up and expose the surface of the water to the air so that it is going to be able to go and lose its heat. You take it sometime, take a cup of hot water and just let it stand. Boil it so you get a little bit of steam coming off of it. You don't see a lot. You start stirring the cup, all of a sudden you see a lot more steam rising because you're releasing, others bring them to the surface so that they can release that heat. We get the same thing inside of here, so my water pumps up through here, we pump it to the top, and then it spills over top of this, and then we get all of that steam that is going to be released, the heat out of these things. It's your chiller tower. It is only going to go and remove high amounts of heat in relation to your outside atmosphere. If your outside atmosphere is 20 degrees, you would be able to go and release anything that is hotter than 20 degrees, but you'll never be able to take your temperature below 20 degrees using something like that. If we do want to actually heat and cool, what we need to use is something that is going to be referred to as direct expansion. Now, direct expansion on large buildings is going to be composed of multiple direct expansion evaporators and condensers that we are going to have. If we go back to our rooftop unit, they're all going to be inside of here. That direct expansion is going to go and have your evaporators and your condensers that are going to be inside of an actual grid, a radiator that will be in the center. So all the air has to pass through that. They're very common over there. You will have two main components that are going to be there. We're going to go and have the compressor, which is going to go and build pressure. We are then going to go and have the expansion valve over here, which is simply going to go and be a restriction in the line. There's nothing, no great amount of magic to it. All it is where we have got, the pipe that's coming through to there, and then there's just a tiny little, they refer to this thing as the orifice, or a tiny hole, where we are going to be able to go and press all of our high pressure on this side through onto that side. And because it's only a tiny amount of little hole. It's going to drop to a low pressure on the other side over here. Direct expansion deals with the fact that heat always tries to go from areas of high heat to areas of low heat. They will always go, you'd never take a cup of water and put it on the counter and then it gets hot by the time you walk away. You always take a cup of water, or in my case coffee, because I'm so busy talking I never get a chance to drink the cup there. But you place it there and then by it releases its heat. It goes someplace else. When we go and run something like this, what we'll do is we'll take a gas that boils off at a low temperature, and then we are going to go and compress it. So we're going to go and have free gas inside of these lines over here. They're sealed. We're going to have free gas. We're going to go and compress it on this side because the orifice is preventing it from necessarily flowing all the way through. We will build to high values of pressure that we are going to have inside of here. That high value of pressure is going to go and results in a lot of collisions between my atoms, right? Because they're pressurized, that means that they're all pressed closely together. Okay, these aren't electrons, these are atoms that are going to be pressed tightly together, which means that they are going to go and bang up against each other, and they are going to, therefore, there's going to be a lot of heat off of them. Energy cannot be created nor destroyed. It can only change form. So as soon as we start all these collisions, we create more heat that we are going to have, which means we have to be taking that energy from somewhere else. We're going to take it from the actual gas itself. We create those collisions inside of here. It starts out as a really high temperature, right where it leaves the compressor. That pipe is supposed to be hot, for those of you that have ever put your hand onto it. It is going to go and send us out as high pressure that we are going to have. It's going to be high pressure vapor that we are going to have. That high pressure vapor is going to go through a coil, a radiator. We're going to call that thing the condenser. And inside of that condenser, as it runs up against the side, it's going to go and release its heat. We're going to have a fan that is going to be pressing air over top of it. It's going to release its heat and it's going to condense. Same as, if you boil water and you hold something over top, you can collect the steam. That's condensation that's happening. So it starts to condense and it forms liquid. And so it goes from being really hot and a vapor to being warm, drop down over here, and it is going to go and be a liquid over here. So we start with a gas. The gas condenses. As it condenses, it's bleeding its heat to the outside atmosphere. It is still going to be high pressure. The whole system on this side is going to be high pressure. They've got 340 psi over here for this whole thing. But by the time it gets down here, it is not going to be as hot. Still the same high pressure, but not as hot, and it is now going to go and be a liquid. And then we pass that liquid through the orifice over here. I want you to imagine that you got your mouth full of water, and then you do that, the thing as a kid, you fill your mouth full of water and then you kind of like spew it out and it comes out sort of as a mist at times, right? What's happening is you're actually able, by dropping the pressure, it's high pressure inside of your mouth, as you send it out, some of it is evaporating at that point. We're going to go and send it through onto this side, and as it expands, it is going to go and drop its temperature. This is just what it is. We've got a high temperature over here because of all the collisions. Now all of a sudden we don't have collisions. It is still that same gas, and because we have lost those collisions, that liquid is going to go through into here, where it's now going to be a low pressure. Now it's a special liquid. This is not water. It's going to be things like freons that we are going to go and have inside of there, or other types of refrigerant. That refrigerant is going to go and evaporate, which means that it's going to change back from being a liquid into a gas over here as it goes through. So we've got cold, 5 degrees over here, low pressure liquid. That low pressure liquid is going to go and evaporate, and as it evaporates, what's happening is, once again, we are going to be releasing. So we are going to go and have hot air, or room temperature air. That's what's inside of the center over here. I'll just erase a bunch of other stuff. That room temperature air gets pushed over top of here. As it gets pushed over top of here, it is going to go and heat up this liquid, which causes it to evaporate inside here, and also causes that liquid to go and rise in temperature. You'll see that from the bottom of my coil, 5 degrees, to the top, I'm seeing a 5-degree differential over here, because I've taken my warm air, pushed it over top, and caused evaporation and caused a rise in heat. That is then going to go and now become a gas, a vapor, and it's going to, as a vapor, hit the compressor and it restarts that entire cycle over there. So it's just a continuous closed loop cycle of gas, easily evaporated type of gas, that is going to go through these. One of the beautiful things about this system is really going to be the mirror imaging. If I look down the center, there's really not a lot different from this side, what we call the evaporator or the cold side, to this side, what we call the condenser over here. All that is different is the direction that we're pumping through there, which means that if I have got a reversible motor, what I can do is I can go and reverse the flow, and I can make this side over here my hot side, and this side over here, this just becomes my cold side over here. All that I am doing at that point is just going and reversing that direction. Some types of pumps and compressors can be reversed. Other times what we'll do is we will just go and have a set of valves that are going to go and be reversible from one side over to the other. That one there, oops, let me draw this one here, like that. So I'm going to go and have a valve here and a valve over here. And what I'm able to do is a valve here and a valve here. So 4 valves like that. If these 2 valves here are open, then I'm going to, if my compressor is always pushing out in that direction, I'm going to be able to pass through, have a hot one over there, have a cold one over there. But if I were to go and close those valves and open these valves up top over here, so we'll open that valve, and then we will close this valve and close that valve. What I would see is, once again, because my pump is pumping out of there, now my pump would be pumping out and pushing that through in this direction, and I would be able to push all the way through from here. It would then be able to go back in. So my pump can still run in the same direction. It's just a changing of the valves, but I can interchange when I have got which side is going to be hot, which side is going to be cold. This is what we refer to as a heat pump. A heat pump is either a reversible motor that is going to go and change which direction we're moving it, or it's going to be a set of valves that is going to go and change where I am running all of this stuff through. All right. That's your basic direct expansion inside of a unit that we would go and have commercially. This, if I'm trying to go and chill something down over here, this duct, or this section is going to be inside of the duct. This is going to be out on the roof. This is where I can go release it to, the outside atmosphere. I'm just going to go and have a bunch of piping that's going to go and run to my actual ducts, and then some that's going to run back up. Inside of my rooftop units, that's all going to be inside of the same section. I'm going to go and have, once again, that evap coil is going to be right inside here. And then I'm going to go and have another subsection of this. Let's kind of just section that one off over there. And this subsection is then going to go and have my condenser coil. If you buy these things ever when they're operating, if it's the middle of summer and you've got an AC unit running, the air that is coming off of it on the roof is hot because it is energy that is not created or destroyed. It's just changing form. We're removing it from inside of the building and taking it to the outside. It's an incredibly cool system. All right, pumps that we are going to have inside of these systems are going to be, in a lot of cases, variable speed, because by varying the amount of speed, I'm going to be able to vary the amount of pressure and vary the amount of refrigeration, so that I don't need to go and have full refrigeration. I can go and adjust that. There's going to be sensors all over these pipes and stuff as well. We're also going to have a number of different types of valves that are going to be used inside of these. Now, these direct acting and reverse acting valves are going to be some of those valves that we would see for us to be able to go and create that heat pump, interchange some of these ones. Direct acting valves are basically like if there's a hole and then this thing is just going to go and plug that hole. It just fights back. It directly acts against whatever the flow is going through that. Reverse acting is going to go and pull up against whatever that flow is going to go and be. So one pushes up against the flow, the other one pulls up against the flow. But those would be what we refer to as being our two-way types of valves that we are going to have. We also have some that are going to be in the opposite direction, where we are going to go and have the actuator, where the flow is going to be in the opposite. Oh, yeah, I guess I can't erase that. That's part of the book. But where the flow is going to be in the opposite direction, where it's actually going to go and aid. We'll have a large flange on the top over here that's going to help hold this thing sealed. They are harder to unseal, though. Same with these ones over here. I could be flowing in like that, and then it is going to go and hold that seal. It's going to pressurize it directly into that. The tops of these, by the way, are just going to be placed inside of magnetic coils. We call those things solenoids, right? Once we magnetize that coil is going to try and attract any chunks of iron, that's going to be this section over there, into it, which would then cause this thing to go and activate. Or in some cases, we are going to go and have two coils, so we can go and have it activate open, activate close, that we would have off of them. We're also going to go and have mixing valves or diverting types of valves, which are going to go and be three-way valves, where we're going to have a single outflow or we are going to go and have a single inflow. This over here for a mixing valve, we see that we have got an in over here that can go in like that, or if I push this down, that would go and seal to the bottom over here, like that, and when it does so, that would open up the hole up top here so that I can go and feed in from here. I can either have them fully open, fully closed, or I can have them proportional, so I can get from two different types over there. This could easily be a hot and a cold, so that I can go and adjust the temperature that's going to be going to one of my condenser coils that's going to be inside of, or my heating or cooling coils that are going to be inside of my actual HVAC system. Same with these ones over here. This is where I'm going to have a single in, and then I can go and divert to multiple outs. This thing has got that triangles there on the top, triangles over there, and if I were to go and push this thing down, I would be able to push it all the way down to the point where it would go and block that out and would send everything out over here, or where I could pull it up so it can go and send everything through there, or partway in between so I could send to both at the same time. All right. Last section of this one refers back to that drawing. They started you out without telling you what it was. Now by the end of it, they're like, oh, hey, let's go and talk about the actual drawing itself. We have gone through everything that is going to be inside of here. They start going through these now in depth with the individual components. We started at the very beginning with the overview rather than waiting to the end to go and do it. But let's just go through what they talk about inside of here as well. Just in case there's any points that I missed and should have highlighted or something like that. Erase all that, give yourself some room. Okay, they start with our mixed air controller. This one over here. Because this is going to go and sense what is my air temperature that I'm actually at. And based upon that air temperature, then we are going to go and adjust, right? We're going to make some of these adjustments to anything that is going to be our air that goes out into the supply. Supply air is always going into the living area. Return air is always coming back out of this one. It is going to go and be downstream of my filter and of my fan, and it is going to try to maintain a set temperature inside here that is usually going to be a target of 13 degrees. Now, these are hard and fast numbers for most commercial systems because usually we've got a set temperature inside of a building of 21 degrees. So we are going to, work with some of these other ones because through years of trial and error, people have discovered that maximum efficiency of these systems usually happen when I start with about 13 degrees here. That way, if I got to heat or cool, I'm not too far out from either one of those. I'm going to try and achieve that by either if I've got way too much heat coming in from here, based upon what my outside air temperature is here. If the outside is cold and my air coming in from the building is hot, I'll just divert some of it outside, take in some cold from the outside, etc. I do also need to go and have that minimum position that is going to go and give me that minimum healthy amount of fresh air inside of there. They talk about economizing inside of here as well. Economizing or economizer control is basically recycling. You have it inside of your vehicle. Everybody has it inside of their vehicle where you've got that option where it shows that arrow that is either coming into your vehicle, usually right in through the windshield for some reason. I don't know, I'm drawing cars poorly because I'm not very good at that. Or alternatively, your vehicle might have the one that shows the arrow like that. Economizer is going to be where I'm taking the air that's inside the car and recirculating that. We do that on really cold days or on really hot days to maximize our AC or our heat that we're going to have. Free air or free cooling is going to go and be where I'm taking in from outside. They call that whole section the economizer. Room thermostat, we did talk about that one as well. The room thermostat is just going to go and say, this is my temperature where I have people, and now I'm going to go and compare that to my supplier, what I have inside of my ducts. And if what is inside of my duct is the same as what I need inside of my room, that's perfect. But if what is inside of my duct is too cold, I should probably heat it up, and I will do that by toggling the heating coil. And then that's going to heat up the air so that the air that I'm sending to the room is going to be the same. It's going to be a comparator system that's going to work inside here. It's all controlled digitally inside of these. Same with if my room temperature senses that it is too hot. Whatever I've got inside of this duct over here is too hot. When it compares it to what we've set the room to go and be, it is then going to go and activate this motorized valve to cool, send cold water through those coils over there. These valves do also have default states that are going to be associated with them. If I take a look at this one, it's got a normally closed state. This one over here has got a normally open state. What we want to have happen is if there would be a failure of, this whole control sequence over here, what I would want to have happen is if there was total loss of power to these, not to the whole building, but just to these over here, I would rather have hot going in because it's not going to freeze out any of my plumbing, rather than cold, because if I return only chilled water, that water could be too cold and it could actually freeze out and cause massive problems. So we do have a default state that's going to be to those, same as what we had for these ones over here. Freeze stat is just going to go and shut off. It's going to be wired to the magnetic damper for my supply fan, this one over here. If for whatever reason, we were taking in way too much cold air and it was getting too cold, this freeze stat over here is going to go and ixnay the fan over there. The fan has to go and shut off so that it is not going to go and put too much cold air in and freeze out any of our coils. Last thing that they don't talk about inside of here is going to go and be just the actual control system. We're going to take a look at the control system yet coming up once we start taking a look at some efficiencies, because at this point we've got very few manual systems. Almost all of these are going to be done through individual modules that are going to just take each of these individuals in and run them out to the last sections. Heat pumps, we've talked about that one as well. That's one of the last sections inside of yours, inside of your module over there. And then the last little blurb over there is one paragraph long, and it says control circuit wiring. Highlight that. They're often going to be low voltage and low current, which means that they're usually going to be a Class 2 circuit. We're going to look at that in code this week. Class 2 circuits being limited to 100 VA of total power. All right, that covers us off for commercial HVAC components. On we go.